The paper presents a novel theory of feature learning in deep neural networks, proposing a spring block model that accurately captures the dynamics and phase diagram of feature learning. This theory is based on the concept of data separation, which measures the ratio of variance within and across classes in each layer. The authors show that DNNs define a family of phase diagrams, where increasing nonlinearity results in increasingly concave load curves, with deeper layers learning better features. Adding noise to the dynamics rebalances the load across layers, while further increasing noise leads to convex load curves, with shallower layers learning better features. The study also highlights the importance of an appropriate learning rate for achieving equiseparation, as demonstrated by He and Su. However, the addition of nonlinear activations breaks this balance, requiring additional ingredients to maintain equiseparation. The proposed spring block theory explains why some DNNs are lazy and some are active, and how the distribution of feature learning over layers relates to test accuracy. The phase diagrams are universal with respect to the source of stochasticity, including varying dropout rate, batch size, label noise, or learning rate. These findings significantly generalize recent work on neural collapse and the law of data separation, offering a clear intuition for why and how some DNNs exhibit non-uniform distributions of data separation over layers, and how this affects generalization. Here is a combined summary of the 2 pages. The paper presents a spring block theory of feature learning, which reproduces the phenomenology of feature learning in deep neural networks, DNNs. The authors illustrate the analogy between a spring block chain in a DNN, where the signed elongation of each Hoekian spring represents data separation afforded by each layer. The equation of motion for the position of each block is given by a stochastic dynamics equation, which includes friction and noise terms. The friction term models the effect of dynamic nonlinearity on gradients, while the noise term represents stochasticity from mini-batching, dropout, or other sources. The authors show that the proposed model results in a phenomenology analogous to that of data separation in real networks. The phase diagram of the spring block system exhibits a striking similarity to the DNN phase diagrams, with concave, linear, and convex load curves emerging under different conditions. The load curve reflects how much each spring, or layer, contributes to explaining the total data separation. The authors analyze the model in 2 regimes. First, without noise and friction, the system is linear with a trivial unique equilibrium, corresponding to the state of lowest elastic potential energy. However, adding friction breaks the symmetry, resulting in an unbalanced equilibrium, where the friction at each block absorbs some of the load, leading to a concave load curve. This corresponds to lazy training in DNNs, where the deepest layer does most of the separation. Second, with noise, the effective friction is redefined, and the load curve can be approximated by substituting the effective friction into the equilibrium equation. For large noise, the load curve is concave if the sliding friction is greater than the maximum static friction, linear if they are equal, and convex if the sliding friction is less than the maximum static friction. This explains the entire DNN phase diagram, where high nonlinearity and low noise result in concave load curves, balanced nonlinearity and randomness result in linear load curves, and low nonlinearity and high noise result in convex load curves. The authors also discuss the connection between the spring block model and DNN phenomenology, particularly the role of noise in propagating from shallow to deep layers during training. The condition of asymmetric friction in the spring block model, where the sliding friction is greater than the maximum static friction, is related to the DNN phenomenology, where noise chiefly propagates from shallow to deep layers during training. The study explores the dynamics of deep learning through a phenomenological model, inspired by the spring block system, which captures the interplay between nonlinearity, noise, and depth in deep neural networks, DNNs. The model reveals that a uniform load distribution, corresponding to a linear load curve, yields the best performance in terms of test accuracy. This is exemplified through an experiment on a deep convolutional network, CNN, on the fashion MNIST dataset, where introducing dropout causes the training to resume and the load curve to become linear, leading to improved accuracy. The authors argue that deep learning theories can benefit from both bottom-up and top-down approaches, drawing parallels with fields like physics, biology, and economics. They demonstrate that their phenomenological model can provide valuable insights into feature learning, an essential aspect of modern DNNs. The model elucidates the role of nonlinearity and randomness, suggesting connections with generalization and conjectures worth pursuing rigorously. The study also reviews various works on neural collapse, data separation, and feature learning, highlighting the importance of considering depth, nonlinearity, and noise simultaneously. The authors draw inspiration from analogies such as the Borage-Napoff model in seismology and related ideas in neuroscience, which have played important roles in understanding complex systems. The paper concludes by emphasizing the significance of phenomenological models in deep learning, which can serve as valuable tools for applying intuitive physical insights to complex, abstract objects. The authors suggest that their model can help guide training to find better networks and improve generalization, and that it may lead to exciting connections with other areas of research. The pages discuss the geometry of neural network loss surfaces, the continuous formulation of shallow neural networks, and stochastic gradient descent. They highlight the importance of understanding the optimization landscape for deep neural networks. The authors introduce a spring block theory to describe feature learning, which is supported by experiments with a folding ruler and numerical simulations. The theory suggests that the imbalance caused by friction can be renegotiated by noise, leading to a more uniform distribution of forces across the layers. This is analogous to the process of training deep neural networks, where the outer layers typically take the largest proportion of the load. The authors also discuss the role of batch normalization and its impact on the training dynamics. The numerical experiments demonstrate the effect of different parameters, such as learning rate, batch size, and dropout, on the training process. The results show that the use of adaptive batch normalization in specific parameter settings can lead to smoother and more predictable training curves. Overall, the research provides insights into the optimization landscape of deep neural networks and the role of noise in the training process. The authors explore the phenomenology of neural networks through the lens of regression and the spring block system. In the context of regression, they define the load as the mean squared error of the optimal linear regressor from the LTH layer features, denoted as DL. This load exhibits a convex curve under noisy training and a concave curve under lazy training, as illustrated in Figure S2. The spring block system is introduced as a second-order system, where the force flat is rewritten to incorporate friction, resulting in equation 9. The friction fluid is dependent on the force Fl and velocity xl, with three distinct cases: sliding friction-resisting movement, static friction compensating for other forces, and zero friction when the block is stationary. This is summarized in an activation-like form, sigma, z, x, in equation 10. The phase diagram of this system is presented in Figure S3, showcasing the load curves and elastic potential energy. The authors discuss the noisy equilibria and separation of timescales in the spring block system. Without truncation, the trajectories exhibit two stages: an initial stage dominated by the elastic force and a later stage where the spring force is balanced with friction. To avoid this, the authors propose three methods: assuming bounded noise increments, applying noise decay, or introducing a stopping criterion. An alternative formulation of the spring block system is presented as a second-order Langevin equation, where noise is added to the velocity independently of friction. This results in equation 11, which can be solved using standard SDE integration. The phase diagram of this system is shown in Figure S4, demonstrating similar behavior to the original formulation. The authors highlight the importance of noise decay to ensure convergence in this formulation. Throughout these pages, the authors demonstrate the connections between neural networks, regression, and the spring block system, providing a deeper understanding of the underlying dynamics and their implications for deep learning.